All right. Welcome, everybody. Today, we're going to continue with the theme of brain-inspired architectures. And it is my great pleasure to introduce Ali Behrouz, who's joining us from Cornell, if I'm correct. You're a PhD student in Cornell and also a visiting researcher in Google, right?
Yes,
Okay.
yes.
Thanks for joining
Thank
us.
you.
Yeah, first of all, I think I want to ask you, is that fair to describe your model as brain-inspired architecture?
Uh, Honestly, it really depends on like what brain is inspired mean, honestly.
Yeah.
If yeah, we received honestly a lot of like emails from like both opinions when we publish nested learning. A lot of like neuroscience people reach out, and some of them say that's exactly what we think how brain works, and these are the papers that say these things. And we receive a lot of things saying that everything that you have said is wrong about brain and so on and so forth. If I want to be honest, our claim was not exactly this, that the brain is working exactly like how we design these models. But I personally think that we should get inspired from the brain in a right level of abstraction. And that right level means that there are some underlying rule in the world.
Mhm.
And we can use and observe our brain and understand what are the limitations and how potentially we can solve them. But the details of the implementation about like how those mechanisms could work might not be exactly the same. So yeah, I think
That was a
it really
perfect
depends.
answer. And about the earlier, the polarization you experienced, welcome to the club. I think that's a sign you're doing something right. So, um, maybe okay, let's start with before we get into the technical presentation, I wanted to ask you to maybe introduce yourself a little bit and tell us about your research interests and basically what kind of questions you're trying to address and what led you to this line of work that ended up, with discovering this nested learning and then the Miras framework and so on.
Sure. I'm Ali Behrouz. I'm PhD student at Cornell and also student researcher intern at Google. And I started my research on like generally the concept of sequence modeling and how we can design architectures that are more capable of doing long context understanding. But over time, I realized that there are some connections between different concepts, and I personally really like to uh, get inspired from the work, not just brain. I mean, everything is a great source of inspiration. We can like learn a lot of things from a lot of natural things around us, and but specifically for getting inspired from the brain, I really like that. And I personally think that one of the main reasons that we have a lot of amazing papers in machine learning in 2013 to 2018 or so was because, if you read a lot of like amazing papers at that time, they have a section talking about like how this specific concept can be related to one of the things that we know about brain and something like that. And I think that's amazing. But that's unfortunate in my opinion, but maybe others might think the other way. After like 2018, there is a huge focus on the efficiency side of model
Mhm.
rather than the effectiveness of these models, how we can like make the models more effective and more useful, more sample efficient, and address some of the challenges about the effectiveness of these models rather than the efficiency. I think when we condition on the efficiency,
Mhm.
then we need to condition on the architecture, we need to work on efficiency. But first we need to find the architecture and then try to make it efficient, not always focus on the efficiency part. I personally try to like work on models that are not as efficient as other architectures that we are seeing.
Mhm.
And one of the main reason is that they can perform more computation per each of the artificial neuron that we have in the architecture. For example, there might not be as efficient as in training, but they might be like more data or sample efficient than what we have because they perform more computation internally. And so generally, like this direction started with Titans architecture. We wanted to like design something that has like long-term memory. At that time, I was thinking that, it's very hard to like hallucinate about the information that I just got in the past 20 seconds. Even if just like tell something, for example, talking about some unknown languages, I can simply repeat that. So it seems that there is like a very, very clear understanding about like a 20 seconds ago, which potentially is in the short-term memory. But on the other hand, we have like longer term memory, and that part becomes more challenging because we go to like longer term memory, but with the cost of forgetting. For example, I might hallucinate about some of the details in one of my old memories, or for example, I might like forget something from the past, and so on and so forth. So generally, like there is a trade-off between these two. And it was interesting for me that, this trade-off, it's very simple to the trade-off between attention and RNNs, because attention is very accurate. It cache all the tokens, but it cannot like scale to super long sequence. But on the other hand, RNN can scale to arbitrary sequence, but it comes with the cost of forgetting and compression. So that was the main intuition for the Titans architecture. So how we can like combine these two together, so they can work in a harmony somehow. Uh, and so like when we were designing that, we realized that there are some interesting concepts that we can like, there are some interpretation for that. For example, if we use gradient descent, if you look at the gradient part, it's somehow a measure for the surpriseness of the event. So for example, you can say that the more your data is different, the larger the gradient is. And in that case, if we look at the processing, we can also like, there are some interesting papers about like saying that usually human brain can prioritize events that are surprising. So there's an interesting connection here. And the main point is why this connection or this interpretation is important. In my opinion, the good thing about that is it shows how we can go beyond that. So generally what we are using is just simple gradient descent, and I'm just like reinterpret gradient descent. But the point is, when I can interpret the gradient part as a surprise metric, I can say that why not using other surprise metrics and come up with like more advanced learning rules, and so on and so forth. So Titans, what was inspired based on that. For example, instead of like gradient descent, we use gradient descent with momentum, saying that the surprise should not be only on the current tokens or current event. It should be based on the like a cumulative sum, or generally like a moving average sum of the past events. So generally, like it has started from that side, but there was an interesting connection between like these concepts and optimization problems, saying that, for example, you know, I'm using gradient descent, and what I'm trying to optimize is based on like simple MLP block in the inner loop of the memory. So my memory is just a simple, the memory in the Titans is just a simple MLP blocks, and I'm trying to optimize that with gradient descent. And now the question is, I know that, for example, transformer is better than MLP. So why not, instead of MLP, I use transformer block? And the interesting part there is that, okay, I can like replace MLP with transformer, but on the other hand, I also know that transformers is a form of like bi-level optimization problem. So again, I can decompose that, and now from like a simple architecture with like 2 level, I have a simple architecture with 3 level, and I can like go farther and farther. So the interesting part is that, it seems that we can decompose all of these architectures into a set of nested optimization problem. And then the question for us was that, should we limit ourselves to just nested optimization problem? Can't we have some parallel optimization along with each other? Or for example, what we are focusing on right now is just a simple recurrent formula. And what we have, it's just a simple linear recurrence. And I'm saying that this linear recurrence is equivalent to this optimization problem. And if you look at all of the optimizers, optimization algorithms, for example, gradient descent momentum, Adam optimizer, everything like that. If you think about them, they are also recurrent formula. So there is a recurrence going there. And so from one side, I realized that, there's a connection between recurrence and optimization. And now the optimizer itself is a recurrence of the optimizer itself is a form of optimization problem. So it seems that everything can be like represented as a form of optimization problem. And so that was a time we tried to like work on nested learning, and we realized that like there's an interesting connection between all of the optimizers and architectures.
Mhm.
And why it's important, in my opinion, the important part is two things. One, we can take advantage of our understanding in each of these communities and transfer it to the other part.
Mhm.
For example, if we know something about optimizers and we have not applied that in architecture side, and now we realize that optimizer and architecture are the same thing. They are just applied in different contexts. Optimizer is applied on the gradients. Architecture is applied on the tokens
Mhm.
or the input data. So I can take advantage of all of the understanding that we have on the optimizers and just use that for our architecture and vice versa. A lot of things that are going in the architecture side that I can take advantage of that for the optimizers. So that's one important component. Another thing is that I can go beyond the current architectures. For example, I don't have to limit myself to a simple transformer block with attention and then MLP. And after the pre-training part, I can say that training has the frequency of updates, zero frequency of update, because we don't update it. It's like the you know it acts as a form of like long-term memory without any adoption. But the point is, instead of seeing the memory as a form of short-term and long-term memory, I can see the memory as a form of as a spectrum of memories. So I have like short-term memory, short-term memory, longer, and so on and so forth. There's a spectrum there. And so how we can like model that spectrum is based on the frequency of updates. So it might not be a very great example. I understand that, but I personally like this example, and somehow it can show the how we were thinking. Let's say that you have like a twin on Earth, and there's a spaceship. One of them can like uh, you know uh, go with the speed of light or something like that, and that's a very famous problem. They're a twin and they just had one ice cream together, and it's a great memory for both of them. And then one of them goes to this spaceship, you know uh, go with the speed of light and something like that, and then just come back. When it comes back, then one twin experiences like 80 years of experiences. So that twin might not remember that specific experience of having that ice cream with their twin, but the other one experiences only 1 minute. So they definitely remember every single details about that specific moment. So if we think about like the memory from these aspects, it seems that this spectrum of memory should somehow works very similar, at least in my opinion. For example, the short-term memory is the one that is updating super fast. So it seems that the time goes very fast for that specific memory. And the longer term memory updates very slowly. So the time goes very slow for that memory. So potentially that was the interpretation for us. And so that was the motivation for designing this continuum memory system in the nested learning. So yeah, generally that was the main, like the way that we were thinking about like the architectures that led to this nested learning and continuum memory system.
Perfect. Thank you for this, high level summary. It was very helpful to me, at least, to just understand the big picture. And to be honest, I came to this meeting. I was expecting a unification between architectures and optimization. I wasn't expecting unification between optimization and interstellar. So I think that example actually is perfect. It's just so it makes sense to me. So. With that introduction, maybe we should just switch to the technical presentation. And, we encourage a lot of questions, so I'm sure there's a lot of rich ideas. So maybe let's get started with that.
Sure.
Okay.
So I can skip the uh, introduction. So generally in the presentation, I would mostly like refer to concepts that are mainly discussed in these four papers: nested learning, Titans, it's all connected, and also like Atlas paper. So let me first discuss about like the current limitation of the LLMs and what I personally think is like uh, missing in the current design. So, transformers and understanding that they can scale with the data and like number of parameters has definitely revolutionized our understanding of AI and how we can like come up with new applications and so on and so forth. So basically, the main thing that happened with transformers was that before that we generally trained the model to do one specific task, and it was great. For example, we could like train at convolutional neural networks or generally like other RNNs for video data, image data, and they work great. But it was one for one task specific task that we had at hand. But with transformers, we could come up with like more general purpose systems capable of adapting themselves to different contexts. And that was one of the main reason of their, generally success in the machine learning paradigm. But the point is that there are like a lot of like, challenges in that direction. For example, there's a long context efficiency. The quadratic cost of transformers can somehow, limit us in like designing architectures that are more capable of handling longer and longer contexts. Another thing is about knowledge abstraction, saying that, I can like simply memorize something, but with more compression, I can come up with more generalized rule that can describe the data, but also can generalize to other things. And so generally, this building different levels of knowledge abstraction is also like very important. Another thing is about the robustness of these models. We can see that a simple prompt change in like current LLM paradigm can completely change their performance in one specific task. Another thing is about fast adoption. So generally, like again, current LLMs are not super great when we like describe a new task that they have not seen in pre-training. And for example, we can see like all the benchmarks on RKGI and so on and so forth. And finally, it's a continual learning. And honestly, like with the continual learning is getting like popular these days, and we can see that every single paper that like is published is claimed to be about continual learning. I understand that like everyone might have their own definition of continual learning, but here is mine. I think generally in continual learning we shouldn't have any test or train time. So with that is the model is always in the process that it can learn from the data and also like perform some inference. So there is no like separate time between test or train time, and that I think that's a very like important component in continual learning, because if we just simply want to like keep updating the models, but still there is a pre-training time and so on and so forth, then in my opinion effectively nothing has changed. So I think that's one point about like continual learning. And why this continual learning should be important, because it's just an analogy. I understand that there might be some differences between the actual concepts of anterograde amnesia and what is going on in like LLMs, but there are some similarities there. For example, the anterograde amnesia, when it happens, the person cannot shape long-term memory after the onset of the condition, and so this inability to form new long-term memory results to the fact that the person can, I mean, they just like experience the present again and again and again, and so it's a very interesting like connection. I think the LLMs is very similar. It seems that the end of pre-training is the onset of anterograde amnesia, and the long-term memory, which is NLP blocks or generally like the projection, they are not getting updated, and the attention itself is a form of like short-term memory. So then the model can experience the present, which is the context in the attention part, but when the context is gone, then all the knowledge in the context is gone as well. So that's a huge issue, and the model would experience the present again and again with new context coming. So there is an interesting connection here. And I think one interesting point about anterograde amnesia is that, you know, the long-term memory is still there. The person can keep their long-term memory and they can experience the present. So it seems that the short-term memory is there. But the main issue, there is no transfer between short-term and long-term memory. And so it's very similar to LLMs, you know, the short-term memory, which is attention, is there, MLP blocks is there. But the point is there is no connection between the knowledge in the context and pass it to the long-term memory. So the question is like how we can memorize and, you know, learn from that. And so generally, like all these models that I'm discussing today are based on the concept of associative memory, and you know that it's a very fundamental concept for generally learning. And there is a like very interesting uh, definition I found in one of the neuropsychology literature that's saying that memory is a form of, I mean, is an update caused by an input. So any update caused by an input to the neural network, or to the brain is a memory. And then the learning process is the process that how we can acquire that useful memory. I really like this definition because it's also like very aligned with what I'm going to present about, like how we can like differentiate the memorization and learning process. Technically, we can like think about associative memory as a form of like keys, as a form of dictionary when we have keys and values. And now, learning is a process of acquiring that mapping between keys and values. We want to understand relation and unrelated, the relationship between related and unrelated events. The question is like how we can define the learning process and how we can come up with the great mapping between keys and values that we have. And so in the training, we want to learn a mapping between keys and values, and in the inference, we have a query and new data, and then we want to see how, based on what I already have in the memory, how I can like come up with the proper output for this specific query. And formally we can say that if I can come up with a learning process saying that I have keys, I have values, and then I want to learn a mapping between keys and values based on the data. So it's a learning process. I need to use an objective. Let's say that my objective is L, and this objective needs to measure the quality of the mapping that you want to learn. And so that would be very simple. I want to learn a mapping M, which can be any function, any arbitrary, any arbitrary neural networks or linear layers or anything like that. And then I have keys and values. And if I optimize this objective, which measures the quality of the mapping, then I can have perfect memory if I can like have a loss function with the zero value. And so there are like a lot of examples for this objective, saying that, for example, let's say I see the problem as a regression problem. So keys are my inputs, values are my output, and it's like a supervised learning process. And let's say that M is just a linear function. In that case, MKT is the prediction based on the learned memory, and the value is the output. So if I maximize the similarity of these two, then it seems that there is a perfect mapping between keys and values. So that's one possibility. Another one is the most simple version of the regression problem, saying that I want to like minimize the error. So MTKT is the prediction of the memory, and VT is the actual label which maps KT to VT. That's the assumption that KT should be mapped to the VT. So if I minimize this difference, then I can come up with the perfect memory that matches KT to VT for all of the T's that I have. So generally, like this learning, this associative memory can be modeled as a form of learning process. And now
I think there was a question. Leonard, do you want to unmute yourself?
Mm, so what I'm wondering is this: if your this objective function could be anything, could be like a policy gradient, right?
Yes. Yes, that I mean, this objective is any measure that can measure the quality of mapping between keys and values. Yes. And so now the question is like, you know, what is the relationship between this associative memory concept that I explained and the current architectures? And now let's go with the simple example that I mentioned. If we use this dot product similarity and then try to optimize this optimization problem based on simple gradient descent, then what would happen is, we write the gradient descent formula, take the gradient for this objective, and the gradient would be VT KT transpose. And if I just simply like replace it, I would come up with this architecture of like MT minus 1 plus VT KT in the most simple format. And the interesting thing is that this architecture is equivalent to linear attention. So that's just like one simple example that how optimizing this objective function can help us to design a new architecture. I will go into more details and more examples. So yeah, this is the example that I mentioned. So if we use like this objective function and use gradient descent, then I will come up with this simple formulation of linear attention. Now let's go further. For example, go to the next objective function that I described. Instead of like dot product similarity, I want to use L2 regression loss. And again, I want to use gradient descent. And if I take the gradient with respect to like this memory that I have here, and also this objective function, and simplify everything, then I will come up with this delta learning rule. And so that's another form of architecture that I can come up with.
Can you give
with
us
changing
a little bit of context? So these two learning rules were published without knowing that you can derive them from this approach?
Yes, exactly. Yes. For example, the way that this linear RNN is proposed is that there's a softmax attention, and the main reason that is like the main challenge they discuss is that it's quadratic cost, and what makes it quadratic cost, because I think I have the formulation of softmax attention. Yeah, it's something like this one. Yeah, so generally the main reason that we have like this quadratic cost is that because we first need to multiply ki and q, and the computation of this part needs to be done every single time for each q that we have. But what they mentioned is that instead of softmax, which results to have exponential kernel here, if I replace it with a separable kernel, and what is that? It means that let's say that k is the kernel, k of a times b is equal to k of a times k of b. In that case, they showed that we can simplify this process. And first, because we can just change the order of multiplication instead of like multiplication of q and k and then multiply by vi, we can first multiply kit to vi and then multiply that to k. And if we write like all these mathematical formulation, we can realize that we can come up with this linear recurrence that I mentioned. So the way that they drive this formulation was totally different from what we are discussing here. And the interesting thing is that this perspective can recover all of the past architectures that we are aware of, but also it can help us to go beyond that. So I think that's the main point. So yeah, generally, like again, for the delta rule by Schmidt-Huber et al., they also like design this delta rule based on they wanted to come up with the architecture that can like fix its error before the update, which is this term. It's mt minus 1 times kt means that's the prediction of the previous state of the memory for kt. And if we consider the difference with vt, it seems that this part is the error happening for the previous state of the memory. So they wanted to like somehow incorporate that error in the update rule, and they come up with this delta rule we have here. And so again, here we can see that with simply changing the objective, we can recover that architecture as well. And so yeah. Now, like there are some, like, I think there are some interesting concepts that we can use here when we use this formulation. So for all these models that I mentioned, this linear attention or this delta rule that we have here, generally we are using, and you can just unroll this recurrence and expand it, and you will get M0 at the end. Everything depends on the M0, the initial state of the memory. And that initial state generally is considered as zero. We just like start from zero and start like putting things into the memory. But the point is, with this formulation, this associative memory formulation, we can meta-learn the initial state. So from this formulation, it seems that what is going on for this recurrent formula is a form of learning, between a mapping between keys and values. And if I have a good initial point, then I can make this learning process faster. So I don't have to start from scratch, start from zero. I can start from something that is like more efficient for the learning process. And so basically I can meta-learn the initial state across all of the possible contexts that I can see and come up with a meta-learned state that can make the adoption very fast for all of the contexts. So that's potentially one of the implications of this perspective. And we can just like extend this idea and say that we can formulate any architecture and design more powerful architecture based on this specific paradigm or this specific framework, which we call it Miras. And so Miras is a general framework that helps us to design architectures based on the concept of associative memory. And interestingly, it can recover all of the past architectures that we are aware of, at least in the modern era of transformers. We can like recover all those architectures, but we can go beyond that. So there are some like 4 choices in that. First is the memory architecture. So in the learning process here, you want to learn a mapping between keys and values. If M is a linear layer, then you are learning a linear mapping between keys and values. If you use a deep neural network, then you can model more complex mapping between keys and values, and so on and so forth. So basically, the architecture here is very important. Interestingly, if we look at like traditional models, like state space models, LSTM and GRU, all of them, they are trying to use a vector as the hidden state. And so the memory in the architecture of all of the, or those traditional RNNs is a vector. And then in linear attention and more recent RNN, we can see that that memory architecture is a matrix. But we can go beyond that. We can use multi-layer perceptron MLPs, or we can go to more complex architectures. And so potentially it can help us to have more capacity in the mapping of keys and values. Another thing is this objective we have here. So in this objective, which we call it like attentional bias, it measures the quality of mapping. So since you are updating your memory based on this objective, different definition of this objective can help you to have different forms of memory. For example, if you have dot product similarity, you might come up with prioritizing events that are very different from the time that you use L2 regression loss, and so on and so forth. So again, we can use all of our understanding of different objectives here. For example, you can use LP regression loss instead of L2. You can use Huber loss. You can use KL divergence or anything similar. So, there are a lot of design choices for this. The third choice is about retention gate. So the retention gate says that how far we can go from the previous state of the memory or how much of the information I want to retrieve from the previous state. So we show that like a lot of things that we know from the architecture side, like forget gates and all these kind of things that we heard about in different architectures, are somehow a form of retention gate, but with different choices of this retention. You can use LP regularization, L2 regularization, elastic net regularization, KL divergence, or any other like potential retention gate here. And finally, the question is, how do you want to optimize this memory? Do you want to use gradient descent for the learning, or gradient descent with momentum, or go to like more powerful optimizers like Newton method, second order optimization method, or even find the solution of this optimization problem in a non-parametric manner? Now let's see, like, any choice of these options that we have here can help us to design a new architecture. And you would be surprised that how a small part of all of the search space in this area have been done in the past. So most of the architectures that we are aware of has used vector or matrix architecture, L2 or dot product similarity, no retention or L2 retention, and then use gradient descent. So there is a huge unexplored space to find novel architecture based on this concept of associative memory. And now let's see, right now we were talking about like softmax, architectures, and one of the most important architectures is attention and softmax attention in more detail. So is softmax attention is a form of associative memory. And the interesting part is that yes, it is, and it is a non-parametric solution to the associative memory. So that's the main reason that attention is like it's a model with growing memory, because at each token, it solves a new optimization problem in a non-parametric manner. So potentially the solution can grow with the data that we have. So that's the main reason the KV cache in transformers is growing, which act as an associative memory of the transformer. So how we can recover softmax attention? Let's define the objective, something like this one. So basically what we are trying to learn is just a center for the space of all values that we have stored in the attention. So we are learning this M. And then based on the similarity of keys and the current query, we weight all of the samples that we have in the data. And then if we solve this objective or this optimization problem in a non-parametric manner, we will see that the final solution is this formulation that I have here. I'm not sure that you can see my cursor, but yeah, the right-hand side of the equation.
You can see it, yeah.
Yeah, great. And so, yeah, the interesting part about this, you can just simply replace S with any other like kernel you want. For example, if you use exponential instead of S, function S, then you will recover softmax attention. So potentially softmax attention is a non-parametric solution to this associative memory problem. Or again, linear variants are instances of the solution. For example, the dot product recover the Hebbian rule in the learning, or L2 regression loss recover the this learning rule that we have here. And what is Titans in that case? The long-term memory in Titans is basically just deep memory here instead of linear memory. And then use weight decay in the optimization problem, which would add additional component here that helps the model forget or retain some information. And also, instead of gradient descent, we use gradient descent with momentum. So if we make these changes to this objective that we have here, then we can come up with Titans architecture. And there are like a lot of other learning rules that we can come up. For example, there is like this OYA rule. And the main goal here is that we want to like make make the Hebbian rule more robust. So instead of just dot product similarity, we also like regularize that based on the, the values that we have in the memory. And if we take the gradients, we will come up with this learning rule, which is in the literature is referred to as Oya rule. Or in the Atlas paper, we present a new like learning rule, which we call it Omega rule. So what is the goal here is that instead of in the all past like definitions, we are taking the gradients with respect to the last data we have. So the memory is optimized based on each token, and it's an online learner. Now, instead of like online learning, let's say that I have past K tokens or past C tokens. And every time I optimize the memory, not with respect to the last token, but with respect to the past C tokens. So that's a very like technical definition of that, but we can also like interpret that all other RNNs are trying to memorize tokens. So each token comes, we compress it and put it into the memory. So we are trying to memorize the tokens. But in Atlas or Omega rule, we are trying to compress the context. So instead of just one token at a time, we compress the context at a time. And so it provides like more expressive power to the model. And so again, with that one, we can design more powerful version of any single architecture that we are aware of. For example, instead of linear attention, we can come up with a sliding window linear attention. So yeah, instead of like just the past token, we can come up with the like past two tokens, which would be like this simple architecture. So there's like a huge space to explore all these architectures. And now so far we see
There
that
is a question.
I wanted to ask, does the idea of doing mini batch gradient descent over the context make sense?
Yes, totally. Yeah. Basically, the way that we parallelize the learning process of all these architectures is based on batching the tokens. So generally, batching help us to like, when we have this batch, let me just explain it here. So let's say that I want to like train the model on this specific objective similar to Titan. And every time I need to like take the gradient with respect to the last state of the memory. So for each step, I need to wait for the previous state to be computed and then go to the next one. So it's not parallelizable. But the point is, if I can chunk the sequence, which is very similar to the batching, it would be a batch of tokens. If I chunk the sequence, and instead of taking the gradients with respect to the last state, I can take the gradient with respect to the last state of the previous chunk. So in that case, the computation of the gradient for all these tokens can be done in parallel. And so, yeah, that totally makes sense. Yes.
Thank you.
Thank you. And yeah, so far we have seen that I think there's
one more question. I can read it, Tyler, or do you want to unmute yourself, or should I read it?
Sure, I can unmute myself. All super helpful so far. Really nice, clear presentation. It's great to also hear more general thoughts. It seems like, and I really appreciate the comments earlier on about how we don't just want to memorize data, a data set, whatever it might be, but we also want to compress information in order to learn higher level abstractions, right? When we think about memory in humans and other mammals, it's not just memorization. There's some necessary abstraction that happens. It's actually very adaptive for downstream behavior, inferences, et cetera. All of the formulations that I'm seeing so far seem to be really well suited for memorization, but not necessarily a form of compression or extraction. And yeah, you can memorize a token, you can memorize a context. Again, my naive read of these formulations is that they're really trying to memorize something, except for possibly some implicit constraints in, for example, the size of the memory matrix, where I could imagine that smaller memory sizes means that there are more constraints on capacity, that there's more compression. This seems to be like an implicit form of regularization that might also lead to different forms of compression. Again, I'm not sure if I'm missing anything here, but it'd be super helpful to kind of hear Ali's thoughts about this memorization compression trade-off. As well, I think it would be very interesting to hear what some good behavioral metrics might be for compression or abstraction.
Thank you very much. I cannot agree more. I totally agree that like the process that we have so far is just seems to be a form of memorization. And actually, that's the reason, the Miras framework I mentioned comes from this paper. And one of the reasons that we are arguing in that paper is that we should call this process test time memorization, because everything is just very similar to the memorization process. We are just trying to compress the data in a way that I can like refer to it. And there is no actual learning process. When I explain more about like the nested learning, I will discuss that where I think the learning process would come and what is missing in the current architectures and why they are a form of like a simple memorization. But I totally agree. But I will explain more about like why and how it can become a learning in the
Cool.
nested learning paradigm.
Cool. Yeah, really, really excited about that. Again, it's just like it's like the memorization is obviously helpful already, right? Like memorization is cool. But it just so happens that compression, which you led with, I think is also a really exciting frontier. Anyway, I'm looking forward to your thoughts.
Thank you. Thank you. Thank you. Yeah. And so yeah, so far what what we have is based on like seeing that all of the architectures are a form of like some optimization problem based on associative memory. And now let's go to the other side, which is optimization and generally the concept of backpropagation. And to discuss this direction, let me start with a preliminary example. Let's say that I have a simple linear layer, and I want to train it in a supervised manner. I have data, and for each data, I have the corresponding label. And now, let's say that I want to use gradient descent, simple gradient descent, to optimize this linear layer for this supervised setting. And so I can write the gradient descent in this format. And then I can simplify it using chain rule and come up with this recurrent formula, wt plus 1 equals to wt minus like this term. And now if we look at like this term, what we have here, we can see that it's very similar to the recurrent formula of recurrent formula that we discussed so far. This xt plus 1 seems to be the key, and then this gradient part seems to be the value, and we are trying to map these two together. It's very similar to the previous term. And yeah, we can see that it's like very simple to see like this recurrent formula can be written as a solution to this objective function that we have here. So generally, if we call this term, this objective, the gradient of the objective here, as ut plus 1, because we are taking the gradient with respect to the output. So generally, this is the error of the prediction. Then ut plus 1 equals to like this gradient or the error of the prediction. And then we can see that the solution to this like optimization problem, the learning problem that we have, is generally an associative memory that is trying to understand for each sample in the training what is the what is the error in the prediction. So it seems that generally the learning process that we have always used based on like gradient descent and backpropagation is a form of associative memory that is trying to compress the training data into the parameters and learn how it can be mapped from the data to the error of the prediction. And so I don't want to like go into the details, but for example, this was just a toy example for linear layer. But in the paper, we show that you can go to any deep neural network, and using backpropagation, you can simply see that basically each layer locally is trying to map the input data to the error of the prediction that is corresponds to that specific layer. And so generally, it seems that the backpropagation process is a form of associative memory that is trying to compress the input data. So so far I discussed about like just gradient descent, but again in the paper we have like other discussions about more complex optimizers. For example, instead of gradient descent, we can use gradient descent momentum, or even like Adam optimizer, AdaGrad, or all of the like well-known optimizers that usually like people use for training neural networks. And so there's a discussion about like all of them in the paper, showing that these results happen for all of the optimizer, and basically the backpropagation process that we are doing is just a form of associative memory. So there is a very like interesting, in my opinion, but unfortunate in reality, misinterpretation between linear compression and gradient descent. So there are some discussions in the in the literature about like potentially gradient descent is a form of linear compression, but unfortunately it's not. So the linear compression that we have here is very similar to linear attention. But there is a very interesting difference between these two definitions. In the linear attention, keys and values are given. So the model has a supervised setup. There's a key, there's a value, and it needs to learn a mapping between keys and values. But in gradient descent, the value is not given. The value is based on the previous state of the memory. So the previous state of the memory generates the value for itself, and then it tries to, map the input data to the value, which is the input data would be the key, and the value would be, the value. So generally, gradient descent generates its own value, while in simple linear compression, each value and keys are given. So in the literature, in the literature, usually like the models that generate their own value are referred to as self-referential models. So it seems that gradient descent is a form of self-referential model rather than a linear recurrence. And so what are the like implications and how they are different? So linear compression is parallelizable. You can like simply expand this recurrent formula and parallelize all of the computation. But here you have true recurrent process, and there is no parallelization unless you approximate it using like batch gradient descent or other like methods. But the actual formula is not parallelizable. The way that you map keys to values here is based on the linear memory. But here, generally, you can understand and learn nonlinear mapping and nonlinear compression of keys and values. And that's one of the reasons that why gradient descent is a very like powerful algorithm. So in the paper, we go also like further, saying that like other optimizers themselves are a form of like optimization problem. So for example, for the Adam optimizer, we show that Adam is the optimal solution to this objective. And what is this objective? This objective is trying to learn a good mapping or generally a good representation of gradients, the current gradient, and a global representation of the previous gradient. So one of the main challenges that we have in optimizer is that when we are optimizing a model, we need to properly understand the loss landscape, and it can help us to better find the optimal solution. But the point is, we cannot like cache all of the past state or generally cache all of the past data samples. And generally, this optimization problem is a form of like online learning or batch online learning. So a good optimizer is the optimizer that somehow manage its momentum term in a way that this momentum can predict a global information about the loss landscape with having only the current gradient. And that's what Adam Optimizer is doing. So it's trying to learn a momentum term such that if you give it this gradient, which is the current gradient, it can predict a moving average of all past gradients. So it would be a global statistic about all of the gradients that we have seen so far. And if you find this process using Newton method or generally find it to the optimality, you can see that the results would be exactly the same as Adam Optimizer. Or for example, you can, instead of just like Hadamard operation, you can use an actual multiplication and come up with AdaGrad and so on and so forth. So far, the good results about like all these things is that, we realize that how they're working. So why Adam is so powerful, because it's an optimal solution to this objective, which makes total sense. Or for example, why gradient descent is working, because it's, backpropagation is working because it's trying to compress the inputs data into the parameters of the model and try to map them and understand how the error for each sample is can be computed. So that's one good point. But another point is that when we realize that how they're working, there is a huge space to go beyond that. For example, gradient descent that I describe here is based on this objective function. And this objective function is a dot product of the similarity of the label, which is the value, and also the key, the prediction of the model. Now, instead of dot product, I can use L2 regression loss, which potentially is a more powerful objective to measure the mapping. So if I use that, then I can come up with a new form of gradient descent, which we call it delta gradient descent. So we replace dot product similarity in the definition of gradient descent as a form of associative memory with L2 regression loss and come up with this new optimization process, which we call it delta gradient descent. The main difference between this formulation and the actual gradient descent comes with this. It's generally about like this weight decay component, which memory goes to the direction that is orthogonal to the previous data that it has seen. So potentially it can manage its memory better. And again, we can do the same thing for momentum. We see that momentum again is a form of associative memory based on dot product similarity. And now we can replace that dot product similarity with L2 regression loss and come up with this delta momentum term. And so it's again more powerful. Unfortunately, I don't have an example for that, but in the paper we have a toy example. There's a function we show that like using delta momentum is much more powerful than having just a simple momentum term in the optimization process. So yeah, there again, when we have this perspective, there's a huge space to explore and design more powerful optimization algorithms and momentum term. So far, what we have seen is that architectures are a form of associative memory or optimization problem. Optimizers themselves are a form of associative memory and optimization problem. And now let's think about the general process of the learning and how like a neural network is trying to learn from the data and just combine these two together. So from one point of view, we see that optimizers are a form of associative memory, but their context is the gradient of the architecture. On the other hand, architecture is a form of associative memory, but the keys and values are the token or generally the input data. So it seems that they are the same concepts which are applied in different contexts. The context of the optimizers are gradients, but the context of the architecture is token. Now, the interesting part is the context of the optimizer, which is gradient, also depends on the architecture. So it seems that what we have here is a form of interconnected system. The context of the optimizer is generated by the architecture. So they are not independent. So that's one of the main reasons. There are some, studies, empirical studies showing that, for example, if you train an MLP with gradient descent, that then it works perfect. And if you train a transformer block with gradient descent, then potentially you might face a lot of issues. And the main reason, I mean, there are some empirical observation and some explanation for that, but this perspective can somehow like help us better understand this situation, because, for example, MLP is a very simple architecture, and potentially the generated gradient by MLP can be very simple. And so a simple gradient descent can manage its memory and compress it to like help the model learn from the data. But if you replace MLP block with transformer, then this architecture can generate like super complex gradients, and potentially a simple gradient descent might not be enough to manage the memory or manage the gradients, and potentially we need to use more complex optimization process. So that's one implication. We need to see the learning process and all of the architectures, optimization, everything as a form of interconnected system that each of them has their own gradient flow. Each of them are locally trying to optimize their goal, and so on and so forth. So, if just combine our findings, we can see that an architecture along with learning process is just a form of nested or parallel optimization problems. And so that's just like one implication, and like how it can help with future direction. If we want to be honest, one of the main things that we were dealing when we were writing the paper was that generally, like, explaining all these things might be simpler when we are talking about them, but formalizing them is very hard. And the way that we wanted to formalize this process, we come up with this definition of update frequency. So how it can help us? It can help us to understand the neural network. As I mentioned, we have like different levels, but it seems that each of them has their own context flow. And so based on the length of the context flow, they are updating with different frequency. And it would be very similar to the example I mentioned about the twins and, the moving with the speed of light and so on and so forth. So now, if we think about this process, the most outer loop is the pre-training stage. So I have one sample, and I consider that as a unit of time. So one step in the pre-training would be 1 unit of time. And then, for example, let's say that I have transformer block. So there's a pre-training, and for each sample, I have a context length of L, which is the training context length for the transformer. And in the attention, I need to like perform, all the dependencies of all the tokens. So generally, I need to like for one step of the outer loop, I need to perform more steps in the inner loop. And based on that, we can define the update frequency, which is the number of times that we need to update the neural network per unit of time. And now, there are some, we define this specific notation to somehow formally define everything, saying that, the frequency of A is like, A is faster than B if the frequency of A is bigger than the frequency of B, or their frequency is the same, but the computation of B depends on the computation of A. So now let's think about gradient descent with momentum. So we see that momentum is another loop inside the gradient descent, which is try to compress the gradients. But the frequency of update is the same. For one step of gradient descent, we need to take one step of momentum term. So the frequency of updates is the same, but the fact is, for the computation of the gradients, for the next step, you need to compute the momentum term first. So that's the reason, for example, we say that momentum is the inner loop for the gradient descent and is faster. And based on this definition of being faster, we can, define a hierarchy of neural networks. where the slower network is on the top, and when we go deeper, we have like faster neural networks. And interestingly, there are like a lot of concepts that we can unify with this simple definition of update frequency. For example, if you think about meta learning, you have like bi-level optimization problem. The outer loop is slower and the inner loop is faster. If you think about attention, I mentioned its example. Similarly for RNN, you have like outer loop for one document. You need to go through all of the tokens, so potentially the frequency is L. And again, momentum term that I also like mentioned that. So all of these things can somehow be unified using this update frequency. And so, like,
can I ask a question before you
sure.
move on about the concept that you're establishing here? I think this is super neat, and it also matches perhaps the types of timescales we observe in the brain. As you go deeper in the hierarchy, things have slower intrinsic timescales, and there's empirical evidence for this. My question is about why you choose this kind of discrete different frequencies. Have you considered having different learning rates? So as you go deeper to the network, you have a slower learning rate, but every part of your network receives updates at every tick of the application process.
Yeah, so I think let me like answer that with one simple example. I think generally having different frequency and having different learning rates are fundamentally different.
Mm.
And why is that? Because let's say that I want to like teach the model the answer to one mathematical question, for example.
Mhm.
And then I start like describing a lot of concepts, and it's a like long context example. And in the middle, there are like 10 tokens that I actually tell the model about the answer of the question. So there is nothing more important than that one. And now that's generally the framework. Now let's go to two different alternative ways that we can train. One is about like having different learning rate.
Mhm.
Having different learning rate might cause the model to use a smaller learning rate per step. And potentially, even in the case that we go to super important tokens which actually like tell us about like the actual solution, we use like a smaller learning rate, and it might cause the model to do not understand about like this specific solution.
Mhm.
But having different frequency help us to have a pause. So, we process the data, then there is a pause. I can like recompute everything. I can like, do everything and then go to the next step. And in the next step, I can properly process any information, any piece of information that is important. So I don't have I can like use large learning rate for the part that is like super important, and a small learning rate for the part that is not important, and do not miss any piece of information from the context,
Mhm.
which was the case for the using different learning rate. So yeah, a smaller learning rate, although can delay the convergence and somehow help us to better explore the alternative paths to the optimal point, it cannot help us to actually pause, and still the model is processing the information, but with different learning rates.
Mhm.
But if we use different update frequency, the model would actually pause, and we will see like, the examples that I mentioned about like twins. That would be the same. Let's say that we have like another like siblings, and that one using different learning rates, meaning that they have a very boring life with not so many good memories. So they still might have some form of memory about that having ice cream together, but still it would be very fade, because although there was not so many things interesting, but still there is a huge amount of information in the past 80 years.
Mhm. So your argument is that it's even conceptually not good to have a continuum of learning rates. You're saying that there's something fundamentally unique and important about this discretization in a sense, like, the frequencies is fundamental to this.
Honestly, I'm not like saying that having different learning rates might not be good. I mean, I think generally these two are
Actually, have you
orthogonal.
tried it at all? Have you tried empirically, or you have not?
Yes. For example, for optimizers, we use like, because we have like M3 optimizer in the paper,
Mhm.
and there are two ways that you can design multiple momentum term for an optimizer. One is having multiple momentum, but with different learning rates.
Mhm.
Another way is to having multiple momentum, but each of them with different frequency.
Mhm.
And we realize, I mean, we find that like having different frequencies is more powerful than
Mhm.
having like different learning rates.
Mhm. Oh, that's great to know that there's some empirical evidence. But then, I mean, I really like your relativity analogy with the twin paradox, but I think it breaks because in general relativity, you have this concept of proper time and coordinate time, and the proper time is a continuous time that is experienced by different people in different parts of space-time. There's no sense of discreteness there. It's continuous. So it.
Yeah, I totally agree. I'm not saying that like these two are exactly like the same thing.
I
I'm
know.
just like using that as an analogy to like,
I know, yeah. Just wanted to mention it. Anyway,
yeah.
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 I think there was another question, but yeah, maybe not. Okay, let's continue.
And so I'm not like going into the like formalization of the nested learning systems, but generally like we can formalize this process saying that like how we can define nested or parallel optimization problem, each of them with their own context lengths and context flow and also optimization process and objective. So yeah, now coming back to this part, we realize that based on this update frequency, we can come up with like having different meta learning and let me also like add something here. The update frequency here does not have to be discrete in some sense. I mean, potentially it can be continuous if your data is continuous. So the main reason that right now is based on like discrete definition is because our data is some discrete tokens. But if we could come up with architecture that process the data in a continuous manner, then we can define the update frequency in in the continuous manner. Then and also like each neural in the architecture potentially can have its own update frequency. But yeah. So here I discussed that, for example, meta learning, attention, RNN, momentum, everything like can be somehow unified with this update frequency. But the point is, these concepts are actually different. So how they can unify and how this simple update frequency can describe them. The main point is about the knowledge transfer.
We
So
have
right
another
now,
question. Sorry to interrupt you. Leonard, do you want to go ahead?
Sorry for the interruption. I wanted to ask, so the difference between the different learning rates and the different learning frequencies is that the different learning rates don't necessarily affect each other, but the different learning frequencies affect the interconnected processes.
yes, that's also true. Yeah, I think that's also like related to this knowledge transfer and how we can like define, because when we have a nested system with like multiple blocks, each of them with their own context flow, the question is like how these blocks can communicate with each other. So coming back to the question about like learning and memorization. So if each block is just trying to update itself based on the definition of memorization, it seems that we are just doing memorization because we are updating the model based on a simple, based on that, every single data that comes, we just like, update the model. So it's very aligned to the definition of the memorization, which says that memory is a form of like update based on the input data. And what would be the learning? The learning would be somehow compress this information, coming up with more levels of knowledge abstraction, and then transfer it to another block. So other like components of the model can also like use that. So that is the part this knowledge transfer comes. So we have like different modules, and how with defining different forms of knowledge transfer, we can come up with different concepts. So for example, one way, let's say that, I can like simply generalize this process. So I'm going to like explain for only two levels. Let's say that I have two levels in the nested learning, and then I want to like see how the knowledge can transfer from one of them to another. One example is direct connection of level in a parametric manner. So I have M0 level, M1 level, and then I can compute the output of M0 by putting M1 as a form of parameter for M0, and then compute the output for the M0. So let's just go like to a real example, not just mathematical formulation. RNNs, or generally like recurrent neural networks, are a form of like this knowledge transfer. What is going on is, I said that, for example, let's say attention or any associative memory architecture. So we have like these three projections: keys, values, and the query. In the here, keys, values, and query projections. These parameters are optimized in the outer loop. For example, in LLMs, it's next token prediction or anything like that. And then we discussed that attention goes to the inner loop, trying to solve a local optimization problem or learning between the mapping between keys and values. So we have like bi-level optimization. One is this part, another one is this part. And now how we compute the output, how the output is computed. So the way that we compute the output is by passing Qt to the MT, which is the state of the recurrent neural networks. So how we compute MT is computed in the inner loop. How we use the output of the first loop based on the conditioning on the parameters of the inner loop. So that's a form, in this linear attention, or generally like any RNN, we are learning something locally to map keys and values. And when we learn that over the context, we pass it to the first loop and then compute the output based on the findings of the inner loop. So that's one form of knowledge transfer. From level 2, we are transferring the knowledge to level 1. Another one is the non-parametric. So it's very similar to the previous one, but instead of passing the parameters, we pass the context of the inner loop to the outer loop. This is very similar to transformers. When we want to do the inference for transformers, we condition the output based on what we have in the context. So again, inner loop is the context, outer loop is what we have for pre-training. Another form of knowledge transfer is via backpropagation. So if you think about the layers of the neural network, as I mentioned, when the frequency of, let's say that all of them has the same frequency, but the point is the computation of layer 20 depends on the computation of layer 19. So basically the frequency, I mean, they are also like, in the nested optimization process. And so later layers are slower than earlier layers. But how we communicate, how we transfer the knowledge through different layers in the neural network, it's based on backpropagation. So backpropagation is another form of knowledge transfer. Another thing is based on initialization. If we think about a model agnostic meta-learning, it's a bi-level optimization problem. The inner loop goes through all of the context, and then the way that we transfer the learned knowledge or memorization process in the inner loop and make it actual learning is based on optimizing this expectation here in the outer loop. So the outer loop is trying to learn an initialization that has the best solution. But how this best solution is found is found in the inner loop. So for example, with different form of knowledge transfer, we are coming up with different concepts. If you define the knowledge transfer via initialization, you will come up with meta-learning or model agnostic meta-learning specifically. Or if you define that based on direct connection of levels, you will come up with the, for example, transformer or RNN definition. Or if you define that based on backpropagation, you will come up with actual deep neural networks. or even like other forms. For example, I mentioned that we can represent a neural network based on nested optimization problem, and like higher levels are actually optimizers, lower levels of architecture side. And I discussed that, for example, the architecture is trying to generate the context for the outer loop, which is optimizer, because the gradient comes from the architecture side. So the context of the optimizer, let me like rephrase it in this way. The context of the optimizer is gradient, and the gradient comes from the architecture side. So it seems that the inner loop, which is the architecture, is generating the context for the outer loop. That's another form of knowledge transfer. And for example, we can come up with hyper networks and other like architectures based on this definition. So I think generally one of the interesting and important future work in this form, I mean, in this direction, is about how we can come up with different form of knowledge transfer, because we realize that and the main point is, if I have a loop here or a one level here, how I can transfer the memorization process in this specific loop locally to a more higher loop and like compress it in a way that it comes with more levels of knowledge abstraction. So that's, I think, very important question. And also it can answer the question about like how the memorization and learning are like shaping in this formulation. When we look at one process locally, it's a form of memorization because we are just simply going through the context and compressing. But if we look at that from the higher level loops, we are learning something because we are transferring the knowledge, compressing the knowledge, and going to the higher level loops and aggregate all of the memorization from different loops that we have and coming up with a more general knowledge. And so, yeah, let's go to the implications, actual implications that we discuss in the paper. So, most of the things, oh, actually, I have the example. I forgot that. So, yeah, I explained about like delta gradient descent, how we can design more powerful version of gradient descent with adaptive weight decay or delta momentum. And in the paper, like we have like this specific form example. It's just a toy example. There's a function defined here, and we are trying to find its optimal value. And there are like two optimizers. One is a standard momentum, another is delta momentum. And we are starting from here, and the global minima is here. And we can see that, delta momentum and standard momentum are like performing very similar until this point. And this is the part that it seems there's a drifting process for delta momentum, but we don't have that for actual standard momentum. So momentum just continue its path and get away from the optimal global minima. But this delta momentum can adapt itself and just find the solution much faster. And so why we can see this process? Because because of this weight decay, this adaptive input dependent weight decay. So in the simple momentum there is no drifting, and so even like the drifting that we use is just a static drifting process. So there's a simple coefficient which is a form of decaying in the momentum, but here is inputs dependent. Based on the gradients we decide like how we change the momentum. So that's the main reason it's more adaptive and can find a solution in more complex function much faster.
Can we can we interpret that outer product of gradients as possibly just an empirical approximation of second order, so like Hessian maybe? So it's essentially just trying to approximate. It's just trying to be a little bit aware of the second order geometry of the system. So that is that a good interpretation of why this works?
And I say potentially yes. I mean, it can approximate, but I think there is like a debate in optimization community about like not calling first order method as an approximation of the second order, because
Mhm.
there is no way that we can come up with second order information based on first order information. Even like, but yes, if we just like focus on the approximation part, that's true that it can help more about like the actual shape of the loss landscape and help us to better find the global optima.
Yeah, you're right. This is not even approximating that. It's a very interesting, it just says that try to put some of that momentum in the orthogonal subspace of the direct gradient. So it's like there's this solenoid motion type of, I don't know. There's something very interesting deep here, but I don't know how to articulate it. But yeah, food for thought.
Yeah, thank you. So yeah, that's for example one of the things, and another one is we always talk about like long context understanding in architecture, saying that we want to increase the the context length and how we can perform and so on and so forth. But the point is, the concept of long context understanding is also a thing for optimizer as well, because if in the continual learning setup, I'm always trying to optimize the model in the loss landscape, and I want to always converge to the optimal point at each step based on the input data. And the point is, if I want to find the actual loss landscape, the global optima in the actual loss landscape, I need to understand the global properties and the paths that I have taken so far to find this specific solution. And so generally, long context understanding is also very important for optimizer. And from the point of view, I mean, the associative memory point of view, we can see that, for example, one of the main reasons that why Adam optimizer is more powerful than gradient descent in some of the contexts, it's because it has better long context understanding, and because of the momentum, it can, for example, incorporate longer term information for this optimization process. Another thing, another implication is I discussed that, like how we can come up with titans. It's basically the associative memory that we use deep memory with L2 regression loss and gradient descent with momentum and weight decay. That's the definition of the titans architecture. But now, from that perspective, keys and values are given. So it seems that from like that form of definition of associative memory, titans is a form of linear compression, because it assumes that there's a key, there's a value. I just use a more complicated form of mapping between keys and values and learn how to do that in a more complex way rather than just simple linear attention and other architecture. But now let's say that we make titans very similar to gradient descent. We can make it self-referential titan in a way that the model not only learn how to map keys and values, but also generate its own value in the process. And so I think, yeah, that's generally the main difference between titans and self-referential titans. Another change that we make is that titans was based on gradient descent with momentum, but we optimize the L2 regression loss in self-referential titan based on delta gradient descent that I described. So basically, we have this specific weight decay, input-dependent weight decay in the update of titans as well. Mm-hmm. And we show that it's more powerful than the case that if you use simple gradient descent. Another implication is this continuum memory system. So why this continuum memory system is important, and also like it's also a good example for why having different frequency is different from having different learning rates. Mm-hmm. So let's say, I mean, the main intuition here is that we want to have like a spectrum of memories. So we don't have short-term and long-term memory, but we have multiple memory modules, and each of them are updated with different frequency. And the first one is high frequency MLP block. The second one is mid frequency, low frequency, and so on and so forth. And you can like train them based on any objective that you have at hand for your specific task. For example, in language modeling, it's trained exactly the same way as transformers. So basically, all these NLP blocks are updated using next token prediction in an end-to-end manner. Or you can like use more complex objectives whenever you want. That's completely arbitrary. And now, why it's important and how it can help with continual learning. Let's say that we are in the continual learning setup. So this high frequency MLP block here, it is getting updated more often. So potentially it can face catastrophic forgetting because we are updating so many times. But the point is, we might face catastrophic forgetting in this high frequency MLP block, but the information is still there in the mid frequency and low frequency because we have not updated so far. So the information is still there, and potentially during the back propagation process, this knowledge from low frequency and mid frequency can comes back to high frequency. So it provides a loop in time dimension somehow. You know, if piece of information is important, then through the back propagation, it can comes back from low frequency to high frequency. But if we have multiple learning rate, it might not be the case because we are always updating all of the modules, but with different learning rates. So at some point, like it might face catastrophic forgetting. And so yeah, generally there are a lot of ways that we can like combine these MLP blocks. For example, these MLP blocks can be fully nested. And what does that mean? It means that the initial state of this high frequency is meta-learned through the initial state of the mid frequency, and the initial state of the mid frequency is meta-learned in the low frequency, and so on and so forth. So each of them are trying to meta-learn the initial state of the other one. And so that's basically like one design choice. Another design choice can be, for example, just put them in like series and don't care about their initialization. The initialization of all of them are done in the pre-training or the outer loop, the most outer loop, or the most slower level, and they just adopt themselves to the context they have. So that's another design choice. So there are a lot of ways that we can like come up with this continuum memory system and like combine them. So there are some like empirical experiments. I personally like, I'm not like big fan of this slide. I mean, generally, like we can show that the performance is better than different architectures, and most of these experiments, I mean, the tables are just like short-term memories. From the results in this specific figure, we can realize that sorry, I forgot to like discuss the naming we have here. So generally, the combination of self-modifying titans with this continuum memory system is called hope architecture. And the combination of attention with continuum memory system is called hope attention architecture. Yeah, here, for example, we are seeing that hope shows very good like memory management when we increase the context lengths. And for example, sorry, there's also like another example here that we go to like 10 million context lengths. The problem is needle and haystack. There are some facts in the large context, and then there's a question at the end, and the model needs to like grab all those facts and then combine them to realize that what is the answer is. And so, for example, the model can work perfectly, almost perfectly in the 10 million context lengths. But for example, these ultra large models can like simply fail. I need to like also like emphasize here that the setup for the red and blue lines are different. The blue lines, because they're ultra large models, they have like billions of parameters, hundreds of billions of parameters potentially. So these models are evaluated in the zero shots manner. So basically just like ask a question. But the red lines are different simple architectures as the baseline, and also like hope, and they are evaluated in the fine-tuning setup. So there's a fine-tuning step, and then we do the zero-shot evaluation. And so even like combining hope with other architectures, we can see that like in the ultra large context, like 10 million, it performs much better than the other architectures. But this is the experiment that I personally really like, and I think it shows like the importance of having like multiple levels, and how like this design and this thinking of in the form of nested learning can help. So we have this like continual learning example, and the main like the task here is that we have like two languages. They are like very rarely used languages, and they are not in the pre-training of any model. And so basically they are unseen. And we want to like teach the model in context to learn these languages. And the point is, in the first setup, which is the red points here, we are teaching one language in context. So one language is like this MTOB dataset, and another one is the Manchu dataset. And we teach the model these languages in context, and then at the end there are some like queries we give them, and they just like translate it to English, and then we evaluate the translated English text. So here, in the red points, the setup is we give one language in context and then do the evaluation. And so the interesting part is simple transformer or in context learning can perform very well to learn one simple language in context. And also, like for example, hope it can perform better, but it's marginal. But now let's go to the second setup, which is the blue points. In the blue points, we put the language back to back in context and ask the model to learn both languages in the continual translation setup. And in that case, we can see that ICL or in context learning can like, it just fail in this setup, and the performance drops significantly. And now we have Hope 1. And what is Hope 1? Hope 1 is just Hope architecture with one level of memory, continuum memory system. So we only have high frequency memory in addition to the attention. So generally it performs like a little bit better than in context learning. And then if we use two levels of memory, then we can like perform a little bit better. And if we use third levels of memory, 3 levels of memory, then we can almost recover the initial performance of the model when we have only one language in the context. So that's one way. Another like experiment that we have in this like in context learning setup is based on like some question answering, and the baseline is in context learning and also like dual attention, and we can see that using like multiple frequency can help the model to perform better. And like we vary the lowest frequency in the continuum memory system. So for example, lowest frequency equals to 512 means that we update the model every 512 tokens. Or
can I ask a question? Sorry, before you, I'm still trying to understand what is the difference between in context learning and hope. So in context learning is the weights are frozen, but you're still doing what the standard transformers do. You're learning from the context. But in hope, you're updating the weights as well with the frequencies that are assigned to those.
You're updating only the MLP blocks. Yes.
Oh, just the MLP blocks.
Yes.
Okay.
Yes. So MLP blocks are, in the ICL, generally, all these process, I personally really like to call all the process that we are doing in nested learning as in context learning, because it's actual, what we are saying is that, every level has its own context. And if we are doing a form of learning, so it's in context learning. So we don't need a new term for that. the in-context learning that we know of today and we usually refer to is the in-context learning of attention, which is like bi-level architecture, and the context means the context of the inner loop.
Mm-hmm.
But here we have like multiple contexts. For example, the context of Titans, which is equivalent to the context of attention, and also the context of high frequency feed-forward network, high mid-frequency feed-forward network,
Mm-hmm.
and low frequency. So generally, like in ICL, but one thing that could happen is that, let's say that the context length of the attention is 4K, for example.
Mm-hmm.
Then ICL has access to only 4K tokens.
Mm-hmm.
And then here again in Hope, the self-modifying Titans is a replacement for attention. So basically the update of these self-modifying Titans is also like based on 4K tokens.
Mm-hmm.
But in attention here, we have MLP block, which is static. There's
Mm-hmm.
no change in the weight. But here, instead of MLP blocks, we have 3 MLP blocks. Each of them are updated with their own frequency.
Mm-hmm.
So the high frequency one is updated every like 1K token. The mid frequency one is updated every like 8K tokens, and low frequency one is updated every like 100,000 tokens, and so on and so forth.
And when you're doing this updating for the Hope architecture, you're still using this cross entropy next token prediction loss.
Yes,
Okay.
exactly. Yes.
Perfect.
And yeah, so yeah, generally like this is the results, and these are the papers that I like discussed in the talk. And yeah, thank you very much for your attention.
Thank you. Yeah, I mean, yeah, I have so many questions, so let me just start with, yeah, I really like this line of work because, it's theoretically very rich and conceptually also very rich, but also you're connecting that to actual deliverables such as architecture design and empirical performance, as you showed us. So my question to you is, there's a lot of like threads that you can pull from here. You can try to make the theoretical part a little, I don't know, connected to other parts of the unifying theories that exist elsewhere. Like, for example, anyway, I'll ask you a little more specific, but I'm basically trying to ask you, what is the next thing that you're excited about right now?
Yeah, I say personally really interested in I think it's also like potentially very promising is about like designing different ways to do this knowledge transfer.
Mm-hmm. Mm-hmm.
And so for example, the way that we are right now doing this knowledge transfer is like, there are only like some simple examples, conditioning on the output, meta learning, or generally hyper networks. And but there are a lot of design choices to explore and see like how we can transfer the knowledge from one level to another one, and what is the effective way to do that. So I think I personally really interested in that direction.
Mm-hmm.
Another thing that I think it's very promising is to find the best, recipe somehow for the architecture, because as I mentioned, there are a lot of design choices that you can make, and so it's not clear that what combination is useful. For example, what objective is the best objective that I can come up with for optimizing these models, and so on and so forth. So yeah, I think these two lines are the part that I personally very interested in.
Very nice. I have another question, but if who else wants to ask? Adam.
Maybe you want to mute yours.
Yeah, I'll mute my.
Hey, great. Sorry, we're in the same room. That's a really awesome talk. So thanks so much. This sort of goes back to like the Friends meme that you showed near the beginning, but part of the sort of disjunction between training time and inference time is just like how it makes sense to deploy these models at large scale. And so thinking, for example, about the architecture you showed at the end where you're adding actual MLP modules that are being trained, it seems like on sort of like a use case by use case or context by context basis. I guess the question is, is there like sort of a LoRa-like solution for actually trying to deploy this at a large scale setting? Or how do you think basically about bringing sort of continual learning into a like deployment context, if that makes sense?
Yeah, I see. Like, I think, as I mentioned, like definition of continual learning and what we expect from that is like very different. For example, you can use continual learning for personalization. You can use continual learning for coming up with models with better knowledge over time, so that you don't need to like update them every like uh, one time every year and so on and so forth. Uh, it really like depends on like what we want from the model, but potentially about, I mean, from the technical point of view, it's totally possible to use LoRa or anything like that. But I mean, still, I personally think that those LoRa thing are mainly based on the efficiency concern. And we can combine that with our understanding in the nested learning and coming up with a solution that is both efficient and also like well motivated from this side. And I totally agree that that's a possibility. We have a paper. I mean, it's public, but these days, if you do not like advertise your work, no one would understand that it's public. We have not advertised it probably next week. Yeah, in that work, we are also like using LoRa for efficient updates, but there's a lot of things to do, definitely. I think.
Leonard, go ahead.
Thanks. So if I'm reading this right, are you saying that we have good ways to do in-context learning, but we don't have good ways to do in-context learning and keep sort of the agentic behaviors we want?
Honestly, I think I think we can do in context learning very well, but in my opinion, I mean that's totally biased opinion, but in my opinion, there is a lack of fully understanding of in context learning, because, for example, if we treat in context learning as literally in context learning, as a form of learning process that happens in context, then a lot of terms that we are using these days are unnecessary somehow, because all of them are just a form of in context learning. For example, if we think about RNNs, what is happening? I mean, when we have this associative memory perspective on RNNs, we understand that, for example, what is happening for the update of RNN is that it's a form of in context learning. There's a state, and you have the context, and based on the context, you're updating the state. And when you go to the next context, the state just goes back to its initial state, and so on and so forth. So it's a form of in-context learning. But the main difference between the in-context learning of RNN and in-context learning of attention is that attention has a form of non-parametric in-context learning, but RNN has a form of parametric in-context learning. And I think one argument here is that I think there are two arguments here. One is in context learning in the form of parametric context learning, non-parametric context learning of transformers is good, and it might be useful. And it's also like super powerful. It's the best way that we have so far for the continual learning in LLMs. But still, there are some limitations, because if you have non-parametric in context learning, there is no compression. And when there is no compression, there are some like theories about like Kolmogorov complexity and all these kind of things, saying that if you do not compress that, it's just a retrieval thing. And it seems that in context of the transformers, we are not actually learning something. We are just retrieving some information. But in the in-context learning of RNNs, we are compressing the context. So it's a parametric way. So at least we are learning something from the context. So yeah, I think that's one argument. So one argument is that instead of like looking at architectures as what we are looking at right now, this is transformers, this is RNN, and so on and so forth. We can look at everything in a unified manner without any naming, saying that it's just do I want to use parametric in context learning or non-parametric in context learning? Do I want to use this learning rule or that learning rule? So we don't have to like limit ourselves to like just some discrete choices that people so far has found. That's one argument. Another thing is about like, can only one single in context learning help me to like understand the data better or not? So for example, if I have a continuum memory system, I try to like motivate continuum memory system from the memory side, but the fact is, from the in context learning perspective, it provides like different levels of like understanding of the data, or generally knowledge abstraction, if you like put them in the fully nested manner. So let's say that the lowest network is meta learn the mid frequency, and the mid frequency is meta learning the high frequency one. In that case, we have like different levels of knowledge abstraction in general. So that's another possibility and another motivation for that.
Okay.
Thank you.
We are right at the 2-hour time. So I'm gonna thank there's one more question. Of course, a very stupid question coming up. Just joking. There's no stupid question.
Hey, so a great talk. I have a question. So just make sure I understand this. So your frequency means the weight updating frequency, is that right? And
Yes.
like did you just mention the current transformer can be written as like a stack of high frequency, medium frequency, and low frequency? Could you maybe explain this a little bit more? Like why it can be reformulated that way?
Sure. So generally, like I think I'm not sure whether I have a transformer architecture. I should have, yeah, here. I think in the transformer design, I think we have the extreme point of frequencies. So what we have, let's just focus on the after pre-training. I can also like discuss during pre-training as well. After pre-training, what is going on is that this feed-forward network is static and it's not updated. So it has the frequency of 0. On the other hand, we have attention, and attention is a parallelizable module. So it can fit to the context in just one step. So potentially we can say that the frequency of update in attention is infinity. So we have two extreme points in the design of transformer, one with infinity frequency and another one with 0 frequency. During pre-training, what is happening is different. During the pre-training, the frequency of update for MLP block is 1, because we update MLP block for each batch of data in the pre-training stage. So it's just a unit of time. So the frequency of MLP block is 1. And for the attention, we update the attention every single like context or document which has the context length of L. So the frequency of update is L, and the frequency of update for feed-forward network is 1. And we can say the same thing for the pre-training of RNNs, saying that the RNN has the frequency of L because for each context we have L tokens, and it needs to go through all of the tokens separately. And so basically it has a frequency update of L. And then we have like this MLP block which updated like one time in the pre-training. And now let's go to the after pre-training for the RNN. Still, RNN has the frequency of L because in the L prime, potentially L prime is the context in the inference time. And but on the other hand, the MF block is static.
Okay, thanks.
All right.
Just really quickly, Ali, do you mind if I send you a message about following up on this question around compression and abstraction?
Yeah, sure. I would be happy to
Okay,
discuss.
good. Yeah, I'll reach out to you later
Thank you.
today. Again,
Thank you.
really fantastic talk. This is beautiful work. It's changing the field. People are paying attention. Everybody's excited. It's really great to hear it from your perspective, kind of how you're approaching this work. So looking forward to talking a little bit more.
Thank you. Thank you very much. I appreciate it. Thank you.
Yeah, thanks again, Ali, for this amazing presentation. And I'm gonna upload this on YouTube probably later today or tomorrow, and I'll share it with you. And
Okay.
yeah, that's it. I'm gonna stop recording now.